Hi guys, these are your Intro to Biochem notes for the first theme that we're doing this semester. So let's just start with some basic info, and hopefully a lot of this is a review for you from middle school. But first of all, what is chemistry? Chemistry is simply the study of matter. So atoms are the building blocks of matter. So the nucleus of the atom contains protons and neutrons. So if we think about that, the charge of a proton is positive, the charge of a neutron is neutral. And then electrons are located outside the nucleus, and electrons are negative. So how does chemistry relate to biology? So chemistry is the study of matter, and conveniently enough, everything's made of matter, including you. So what does an atom look like? So if you see here, we have the nucleus, which is all of the protons and neutrons inside the nucleus, and then the electrons are located outside of the nucleus. So elements. Elements are composed of atoms. What is an element? Simply put, it's the simplest substance that's made of the same atoms. You're probably familiar with lots of elements: carbon, oxygen, nitrogen, hydrogen. Those are all elements, and they all have a name and a symbol, which is usually one or two letters, and they're located in the periodic table. So the periodic table itself, this should be something very, very familiar to you. So how is it organized? So it's organized by periods and groups. And the important thing to think about too is, why are protons even important to the periodic table? So first of all, periods are going to go this way. They are horizontal. Groups, on the other hand, are vertical, so they go up and down. And there's a lot of trends and things that go with the periodic table. We won't spend much time on that, but when you take chemistry, you will. And protons are because the atomic number is telling you the number of protons. So if you look closely, the periodic table is arranged by the number of protons. So how to read it? So like I just said, the atomic number is the protons of an element. And in a neutral element, this is also the number of electrons. So if you see here, we have our atomic number, which is 47, meaning silver has 47 protons and 47 electrons. So another thing from the periodic table is the atomic mass. So this is the number of the protons and the neutrons combined. And how do we calculate neutrons? Very simply, in this situation, you would round, so it would be 4 minus 2 equals 2 neutrons. So molecules versus compounds. So a molecule has atoms that are held by covalent bonds, and a compound is something that forms when two or more different elements combine. So let's look at some elements here that form compounds and try to calculate their numbers. And it's really important to keep in mind that they can only be broken apart by a chemical reaction. So how do we determine what's in a compound? You use the letters. So let's check. What elements are in HBr? Hydrogen and bromine. And then how many of each element? One of each. So if you don't see any numbers, just assume one. So let's do a couple more. So what elements are in this compound? Well, this is water, right? So H is hydrogen, and the O is oxygen. And don't mind my handwriting, I'm writing with my finger on my screen. And how many of each element? Well, we just look at the numbers. So there's 2 hydrogen, and there's 1 oxygen. Now this next one's a little bit different. So Fe is iron and O is oxygen. So how many of each element? Well, this you have to multiply. So 7 times 2 is 14. So there's 14 Fe, and then 7 times 3 is 21. So there's 21 oxygen. So chemical bonding. Simply put, what do chemical bonds do? They form chemical compounds. And there's 2 types that we're going to talk about. So the first is a covalent bond, meaning they share it. And an ionic bond is when one element loses an electron and the other one gains the electron as part of that bond. Hydrogen bonding is something else we'll talk about, especially when we get to DNA. So a hydrogen bond is an electrostatic attraction. So it's not that bonding that ionic and covalent are. And it exists when hydrogen's bonded to something that has a high electronegativity. So why are they even important? Well, they're important in properties of water, proteins, and DNA. This is what holds that double helix together. So physical versus chemical. So there's a couple signs of a physical reaction. You probably see these every day. So the texture might change, the shape might change, or perhaps the most common is the state. So an ice cube melting into water, which then evaporates into a gas, is all still a physical reaction because the water has not changed its properties. The chemical reaction, on the other hand, is going to form something completely different with completely different properties, everything that goes along with it. So this is usually shown by a color change, a precipitate's formed, maybe a gas is formed, or an energy change. So for example, when you burn a piece of wood, you can't ever get that burnt piece of wood back to the wood. It becomes ashes, it reacts. That's your chemical reaction happening. So a good test is physical, you can change it back. Chemical, you cannot. Chemical equations then show the process of the change. So super, super important that you remember that the reactants are always on the left side of the arrow and the products are always on the right. And when we balance chemical equations, you need to specifically pay attention to the fact that the subscript numbers never change. You only change the numbers in front. So let's do this one here at the bottom. So we start with 2 oxygen on the left and 2 hydrogen, but the right-hand side only has 2 hydrogen and 1 oxygen. So the first thing you want to do is try to figure out how to make the oxygen equal. So there's 2 over here, there's 0, or 1, I should say, over here, so we can just put a 2 in front, which means you would multiply through. But now we have a teensy problem because now there's 4 hydrogen and 2 oxygen. So our oxygens are equal, but now we have to make our hydrogens equal. So there's a simple fix. You just put a 2 in front of the H2. And we'll do lots of practice with these in class. Energy diagrams are also important for the biochemistry. So this shows the available energy of a reaction. And a really, really, really important term here is activation energy. So that is the minimum amount of energy required for reactants to make products. The whole point of an energy diagram is showing the formation of reactants into products. So if you look here, activation energy is between where the reactants start and the very top peak of that hill. So these reactions, though, either take energy or give off energy, and those are 2 terms called exothermic and endothermic. So which one's which? Well, exo, if you remember, means out, and endo is in. So then exo is going to release energy, and endo is going to take it in. So let's look here. So an exothermic reaction, so the reactants start here, we still have to climb that hill to that activation energy. But if you look, the products are lower than the reactants, meaning there's less energy at the end of the reaction. So this would be an exothermic reaction, and it would give off heat or energy. The endothermic reaction is the other way. So if you look, the reactants start here, we still have to climb that hill, go over that activation energy, but the products are here. So that means that this takes in energy as part of the reaction. Enzymes are also important to these reactions because they help them. So they're a special protein, and we'll spend a lot of time in this course talking about the 4 macromolecules, and protein's one of those. So the catalyst is something that causes or accelerates this chemical reaction. The reaction could usually happen without it, but it makes it more efficient. It's really important to note that adding a catalyst doesn't automatically create more product. It makes it more efficient, so it creates more product in a faster time, but it simply does not just create more product. So what are they? Some biological catalysts that we'll talk about in this class. There's ones in photosynthesis, cell respiration, growth and development, removal of waste, DNA replication, and even movement. So how do they work is what you're probably wondering. So there's 3 parts. There's a substrate, an active site, and then the enzyme itself. So the substrate is what's acted upon by the enzyme. And the active site is probably the most important thing to remember because that is that space in between the enzyme and the substrate. So it's where they bind. And the enzyme itself has the active site, and it can only bond with certain substrates. So you're going to have a lot of processes happening in your body, for example, and you have lots of different enzymes, but they only bond with certain things. So they're not always just going to react. So there's a specific active site that bonds the specific substrate and enzyme. A little bit more. So they only fit specific, like I said. And what happens when it's heated? Well, this causes something called denaturing. So what that means is that the enzyme no longer fits the substrate. So now this is going to cause a lot of problems in your body. And we'll talk about specific instances of this in class, but it can really, really cause some problems. There's also 8 properties of water that you need to know about, and we'll spend time on these in class, so if you just want to write these down, and then we'll go over the details later. Solutions are also important to biochem, so solvent and solute. These are the 2 most easily mixed up things in this unit. So the solvent is what does the dissolving, and the solute is what is being dissolved. And the way I remember it is if you go in alphabetical order, so we go T, then U, then V, U always goes into V, not vice versa. So you're not going to put a solvent into a solute. Also, typically when we think about it, a solute is a powder like hot chocolate. The solvent is your liquid like milk or water. So there's 2 types of solutions. So there's a homogeneous solution and a heterogeneous solution. So the homogeneous, remember the prefix homo means same. So this is going to be a same mixture all the way throughout, like our favorite drink over here from childhood, Kool-Aid. A heterogeneous mixture, on the other hand, is distinct. So if you eat trail mix or a blended rice, or you see even the M&Ms there, all the different colors, it's a mixture, but you can see the different parts, and it can usually be re-separated. The final thing we're going to talk about is pH. So pH, simply put, is the concentration of H+, which means hydrogen, ions in a solution. So acids are going to be a pH lower than 7, so they're this way on the scale, and a base is a pH higher than 7. Hopefully you all realize that water is a pH of 7, water's neutral, and this shows just some common foods and things that you might eat that are on this pH scale, or not eat. Please don't eat, drink, liter, or ammonia, but lemons, apples, bananas, vinegar, tomato, those are all very acidic. Even orange juice, I'm sure you've realized before, sometimes if you drink too much orange juice, you get an upset stomach because the acidity is so high. A little bit more about pH. So if the substance releases hydrogen ions when it's dissolved in water, it's considered an acid. So an acid is that release of hydrogen ions. And then a base is the opposite. So if it releases OH ions when it's dissolved in water, it's a base. And if you remember, water is H2O. So if water's H2O, so 2 hydrogens and an oxygen, so an acid releases the hydrogens to make water, and then the base releases the OHs. And water can behave as both an acid and a base. This is really important to remember, especially because it's neutral, it can be both. And like I said, pure water is a pH of 7. And that's it for your intro notes.